So the last two topics were analysis of covariance and an introduction to factorial ANOVA. Today we're going to talk more about factorial ANOVA, but we're going to follow up the main facts. But before we start on that, are there any short-ish questions that I can address first? If any of you have longer-ish questions based on the last two topics, if there's time in the break, or if we end early enough, if there's time at the end, you can come and ask. Or get in touch with your TA or myself or email. Okay, let's jump in then. Factorial ANOVA Part 2, and this is the second to last week. A note about the final exam. So it's posted on the website as well. It is scheduled for Saturday, unfortunately, Saturday morning at 9 a.m. In UCC. The exam covers the entirety of the course material, right from the beginning to the end. Just like the midterm, you're allowed one cheat sheet, and it can be front and back side. And it should be handwritten, not typed. And I posted a couple of sample questions on the website, but I'll be posting some more as well. The final exam is going to be basically just like the midterm, except it's a bit longer. You have 3 hours for it instead of 2, and so it's just going to be staying a little bit longer and covering more material. So you all did quite well in the midterm. So if you do the same thing, you should be just fine. Okay, let's talk about following up a two-factor ANOVA. So here's some example data. It's fictitious data about a blood pressure drug experiment. We've got a dependent variable, which is blood pressure. So it's a continuous variable. And for blood pressure, lower is better. And the experimenters are testing two different categories of treatment to try to lower blood pressure. One independent variable is biofeedback. Biofeedback is when you show people in real time some kind of display of some physiological measurement like variable like their blood pressure, and you tell them, okay, concentrate really hard and try to lower it. And they sort of go, they use the force or something. That's what biofeedback is. And it kind of works sometimes. So biofeedback absent or present. And then the second factor is drug with 3 levels. Placebo, absent, present, or high dose of the drug. And so we've got 2 factors, a 2-level factor and a 3-level factor, and they're fully crossed. So each category of drug is tested in each category of biofeedback. So we've got 6 different groups. Each group has 5 participants. So a participant only contributes a score in one of those 6 groups. So there's 5 times 6, which is 30 participants in total. So if it's 2 by 3, that's 2 times 3 is 6 different groups. 5 in each group, 6 times 5 is 30. Here's a plot of this hypothetical data. Drug on the horizontal, absent, present, and high dose, and biofeedback is plotted as different line colors, and blood pressure on the vertical axis. Lower is better. So, I mean, the first thing to do before you even do an ANOVA is to look at the data with your own eyes and sort of use your own brain to interpret what might be happening here. And when I look at that, what I see is, well, the effect of the drug is different depending on whether biofeedback is absent or present. If biofeedback is absent, this blue line, then when you give a drug compared to no drug, there's only a tiny reduction in blood pressure. And when you increase the dose, nothing much happens. So there's maybe a moderate effect of the drug, if that's real, but not much is happening when there's no biofeedback. But when there's biofeedback and you give the drug, that's the orange line, then the drug appears to have a big effect on blood pressure. when you give the drug and biofeedback is present, blood pressure drops a lot, and if you give an even higher dose, it drops even more. So that's how I would interpret that with my eyes and my brain. And based on what you learned in the last week's topic about main effects and interaction effects, what do you think is likely to happen there? Is there an interaction effect there, or no? Yeah, there is. It's a classic definition of an interaction, where the effect of one factor, the effect of drug, is different depending on the level of the other factor, biofeedback. There's a big reduction when biofeedback is present, and there's a much smaller reduction or no reduction when it's absent. Classic interaction effect. Okay, so let's say we conducted a two-factor ANOVA on these data, and here's the output of the ANOVA. And remember, when we have a two-factor ANOVA, there's three effects that are tested. The main effect of factor A, the main effect of factor B, and the A by B interaction. So we have the main effect of biofeedback, and it's significant. The main effect of drug, and it's also significant. And the biofeedback by drug interaction effect, and it is significant. And so what's our next steps? Basically, you can think of the next steps as a kind of a flow chart or a tree. And even though the interaction effect is the last thing listed, that's actually the first thing to look at. Because what you do following the two-way ANOVA branches depending on whether the interaction effect is significant or whether it's not significant. So you look at the interaction effect first. If it's not significant, it is here, but if it were not significant, then what you would do is you would look at the main effects. The main effect of A and the main effect of B. One by one, separately. And you would ask, is the main effect of A significant? If it is, then you would conduct follow-up tests within that main effect. Pairwise tests, for example, with appropriate type 1 error correction. If the main effect of A is not significant, you do nothing with that. Then you go to the main effect of B. Is it significant? If it is, then you would do follow-up tests on the marginal needs of B with appropriate type 1 error correction. If it's not significant, you do nothing. So when I say marginal means of A and marginal means of B, what does that mean? What's the marginal means of A? Does anyone want to try defining that? Yeah.
The averages when you ignore the other factor?
Yeah, that's right. The marginal means of A is the average value of the dependent variable in each level of A when you average over levels of B. Or you can say it when you ignore levels of B, or when you combine the data over all levels of B. You just pretend factor B doesn't exist. So you take all the data in each level of A across all levels of B, and you take the averages. Exactly. And the marginal means of B is the same idea. It's the average of each level of B when you ignore the fact that there's levels of A as well. So if the interaction is not significant, then you look at the main effects one by one, and if they are significant, you follow that up with pairwise tests to see what's different from what. If the A by B interaction is significant, and that's the case here, if it is significant, then the first thing to know is don't even bother looking at the main effects. You don't even have to look at the main effects. If the interaction effect is significant, it doesn't make sense to look at the main effects. Does anyone want to try to explain why? Why does it not make sense to look at the main effects if the interaction effect is significant? I mean, maybe there's some conditions where it might be, but in general, no. Yeah, try.
Because the effect of one is directly based on the effect of the other, just isolating it won't actually give us any practical help.
Yeah, so you said because the effect of one depends on the other, then just isolating one doesn't make much sense. Yeah, I think you're 99% there. Oh, we just tweaked the wording a bit. If the interaction effect is significant, remember the definition of the interaction. It means the effective factor A is different depending on the level of B. The main effect of A averages across levels of B, or combines across levels of B. It ignores the levels of B. So why would you ignore the levels of the other factor if you know that the effect of A depends on the level of the other factor? Or to put it in terms of this graph, the main effect of drug would be if you average these 2 points, and you average those 2 points, and you average those 2 points, and you look at whether drug present, absent, or high dose is different when you average across levels of biofeedback. Now you could do that, and in this case, would you still get a significant effect? Well, yeah, you get it. Where is it here? The main effect of drug is significant, but it masks what's really going on, right? It hides the fact that, well, there probably isn't an effect of the drug when biofeedback is absent. There is one where it's present. So if you ignore biofeedback, you're sort of ignoring the fact that, well, yeah, the drug works, but not the same way in both levels of the other factor. So in my mind, it doesn't really make sense to even consider the main effects if the interaction effect is significant. So think about it this way, it saves you a lot of work. Just look at the interaction. If that's significant, that's what you focus on, and you can ignore everything about it and you need to know that. So if the interaction is significant, then a common way to proceed after that is to look at what's called the simple main effects of the factors. So you can test the simple main effect of factor A within each level of B. Or if you want to do it the other way around, you can test the simple main effect of B within each level of A. It doesn't much matter which one you choose. Although one might make more sense than the other depending on the experiment. And what's the simple main effect? It's kind of like doing a series of one-way ANOVAs on A, where you just separate out the data in each level of B. And then for each simple main effect that's significant, you would then follow it up with pairwise tests. Sometimes researchers will bypass those simple main effects in an interaction and just jump directly to pairwise corrective tests. That's okay. For me, that's okay. Some say it's not okay because the simple main effects are there to protect you against type 1 error. They're kind of like a protection. And if it's not significant, you shouldn't go do pairwise tests. Other researchers think, well, no, it's still okay, as long as those pairwise tests that you do are appropriately corrected for type 1 error, then that's what protects you. Who's right? I don't know. It really depends on the situation, how much data, how many levels of each factor, all sorts of things. I don't know that there's even an optimal kind of proof that one way is guaranteed to be always right. So I think the way to think about it, and the way I think about it, is whatever you do, as long as you're protecting yourself against type 1 error in some agreed upon way, then that's okay. On an exam or an assignment, I'll ask you what to do. So in our sample data, there is a significant interaction effect. So we'll do simple main effects tests first, and then we'll do pairwise post-hoc tests on the significant simple main effects. But let's look at some examples of different scenarios that we can come up with. So here's an example where we have a significant main effect of a drug, so placebo, low dose, high dose, and now it's in female or male, I don't know, mice, let's say. And the dependent variable is memory score. So there's a significant main effect of the drug. There is not a significant main effect of sex, and there is not a significant interaction. So remember, the first thing you do is you look at the interaction. Is that significant? No, it's not. Okay. So then the next step is to look at the two main effects. The main effect of drug is significant, and the main effect of sex is not. So let's focus on the main effect of the drug. And remember what that is. That's placebo, low dose, and high dose when you average across sex. So it's like combining these two data points combining those two data points and combining those two. And that's what I've drawn here. That would be the marginal needs of the drug main effect. And you can do pairwise post-hoc tests. Placebo low dose, placebo high dose, low dose high dose, for example. So that's how you would follow up that situation. Questions about that? Here's another example of what might happen in a two-factor ANOVA. So now we still have drug and sex and memory score. We first look at the interaction. It's not significant. Okay, good. And remember from last time, a signature of a situation where there's no interaction is when the lines are parallel. Right? If you draw a two-factor ANOVA in this way, with one factor down here and another factor as different lines, if the lines are parallel, there's no interaction. And that's because each line represents a different level of factor B. And if the lines are parallel, it means this thing, factor A, has the same effect in both levels of B. So no interaction. So again, we look at the two main effects. The main effect of drug is significant, and that would be as if we combine those 2 points, we combine those two, and we combine those two, and we would get marginal needs like that. Placebo, low dose, and high dose, averaged across male and female. And we would test that main effect, that simple main effect, and we'll see how to do that in R in a few slides. If that's significant, then we would do pairwise post-hoc tests to see what's different from what. For the sex main effect, so now we're testing male versus female averaged across all levels of drug. So it's taking the average of all the red dots and comparing it to the average of all the blue dots. So it's just 2 points. The marginal needs of sex are just two needs, female and male. And so once we do that simple main effects test, there's nothing to follow up. It's just 2 points. If it's significant, they're different. If it's not significant, they're not different. And there's no type 1 error correction needed because it's just one test. Here's another situation, which is more akin to the one we had in our sample data. Now we look at the interaction first, as we always do, and it is significant. There's a drug by sex interaction. And that makes sense if you look at the graph. The lines are not parallel. In male mice, there's no effect of the drug on memory. In female mice, there is. Memory score increases the more drug you administer. So we would follow up this significant interaction with simple main effects tests. And there's 2 ways you could do it. You could do the simple main effect of drug within male mice, and that would be like doing a one-way ANOVA on this subset of the data. There's just one factor, drug, and it happens to be in male mice. And then you would do a one-way ANOVA on these sets of data. Placebo, low dose, and high dose, just with female mice. So it's literally doing 2 one-way ANOVAs, kind of splitting the data apart. And if each of those ANOVAs are significant, then you would follow them up with pairwise post-hoc tests. That's what a simple main effects test is. It's the effect of one factor, isolating it within each level of the other factor. Equivalently, you can do simple main effects tests like this. You can do the simple main effects of sex within placebo. Now that happens to be just 2 data points. So a one-way ANOVA with just 2 levels. And then you can do a second one-way ANOVA, isolating male and female mice just in the low dose. And then you can do a third one here. There'll be no follow-up test. It's just 2 needs, just 1 test. Whether you do it this way or that way, it's completely up to you, and it probably is dictated by the nature of the experiment and the nature of the questions you have. They're equivalent. You won't get any more information by doing one over the other. It's the same information. It's just presented in a different way. Now, like I said before, some researchers will bypass these simple main effects tests if there's an interaction effect, and they'll just jump directly to doing pairwise post-hoc tests, whatever specific tests they decide they're interested in, or just do all possible pairwise post-hoc tests and correct for type 1 error and then interpret the results that way. That's also acceptable. I don't know, I kind of like the idea of doing these simple main effects first, especially with this kind of experiment. It makes sense. You're testing a drug on memory, and you're doing it in female and male mice because you think there might be a difference in the mechanism. And so you want to know, does the drug work in male mice? Does the drug work in female mice? That seems like a natural way of organizing the statistical analysis. But you can do it the other way as well, and that will be okay too. Yeah, or you can do, like I said, all possible pairwise tests. And if there's 6 groups, 3 times 2, then there would be 15 possible post-hoc pairwise tests. That's the equation for the number of possible pairwise tests. N times n minus 1 divided by 2, where n is the number of groups. You don't have to memorize that or write it down. I'm not going to ask you about that. Okay, let's go back to our sample data, where we did find a significant interaction between drug and biofeedback. F is 4.664, and the p-value is 0.019. Let's start by pretending that that's not significant, and see what we would do. So if the interaction effect here was not significant, then what we would do is follow with the main effects. We'd look at the main effect of drug, and then the main effect of biofeedback. So to look at the marginal means for the drug factor, that's the mean of each drug group averaged over the biofeedback conditions, we can load up a library called EM means in R, and then there's a function called EM means, where it's kind of handy. We just give it the ANOVA object, the output of our ANOVA analysis, and then a formula. That's a little squiggly line, that tilde drug. That tells us EM means I want the marginal means of drug. Ignore any other factors that are in the data. And so we get our 3 marginal means of drug, 189, 177, 173. And we get some confidence limits as well. To actually do pairwise tests, we can then use the pairs function and feed it the output of this EM means command and tell it how to adjust for type 1 error. And here we're just adjusting using 2D adjustments. And so you get 3 pairwise comparisons. Drug absent compared to drug present, absent compared to high dose, and present compared to high dose. And you look at the corrected p-values, and absent versus present is significant, and absent versus high dose is significant, present versus high dose is not. That's averaging over biofeedback. Remember, that's pretending for the moment that there's no interaction effect. If that was the case, that's how you would follow the main effective drug. Questions about that? Yes?
Oh, sorry. Is there a reason why we use the TD one and not like Bonferroni?
No, I just chose that for an example. But you could use Bonferroni, or you could use Bonferroni home, whatever you prefer. Yeah, in fact, here's how you would use Bonferroni home. You would just change adjust for 2D to home, and you would get the Bonferroni home p-values. In the ideal world, you've done your thesis experiment, you have your data, and no matter which of these adjustments you choose, everything sort of stays the same. That's a really nice position to be in, because then it doesn't matter so much, right? You're not sort of living on the knife's edge. If you're in a situation where you use Tukey, a bunch of them aren't significant, and if you use home, a bunch of them that weren't significant with Tukey become significant, and you want them to be significant because that's your prediction, and you decide, well, I'm going to use Bonferroni home because it gives me what I want, right? then you just run two risks. You run the risk of actually interpreting a difference as not real, because you're sort of choosing the best outcome based on what you want. You also run the risk of whoever's grading your thesis or reviewing the paper you've submitted, or whoever's examining you in a thesis exam, saying, how come you used von Froni home? We all know that, in this situation, two-key correction is more appropriate. And even if you disagree, you might be forced to switch it to two-key. And if everything suddenly changes, like, now I have to rewrite the whole results section, change my discussion section, because I can no longer say this theory supported. That's just a bad position to be in, where your data is sort of on the edge. So just not to go too much on a tangent, but if you are in that situation, you've collected some data, you've done a statistical analysis, and you've tried analyzing it different ways, and depending on what you do, things are significant, other things aren't, and then it changes. What can you do to help yourself get out of that situation? What can you do that's appropriate? There's lots of things you can do that are inappropriate, but what can you do that would kind of help? Any ideas? It doesn't involve any kind of analysis. No? Yeah?
Just pick one and stick with it.
Just pick one and stick with it? Yeah. I mean, that is one approach, is decide on which one you can defend, right? Not defend because it gives you the results you want, but defend for some independent reason. Yeah, you can do that.
Did you run a lit review and see which ones usually used in your case, so then use that one?
Yeah. You said do a lit review and sort of see which ones are used in your situation and use that. Yeah, that's similar to the other suggestion. Yeah. There was, yes.
You just report both of them. In the discussion, maybe mention.
Yeah, you could write two versions of your paper. No, not really. I mean, you could report both ways of doing it, and then you have to sort of say, and so if we go with this one, it means this, and if we go with that one, it means that. It's not very definitive, right? I mean, it might not be definitive in truth, but it makes for a difficult paper to write. I was thinking collect more data. Right? Just in the spirit of the more data you collect, the closer to the truth you get. Go collect more data, and hopefully what will happen is things will become clearer. The things that are actually not significant will always look not significant, and the things that actually are significant will actually look significant.
How can we collect more data without being accused of p-hacking?
Yeah, so the question is, how can we collect more data without being accused of p-hacking? That's a very important point. And so here's how I think about it. Let's say you've run 20 participants, you do your stats, it's muddled, it's not what you want to happen. You go and you collect one more participant. You rerun your stats, no, collect one more. Rerun your stats, no, run one more. Yes, that's what I want. Okay, stop, right? That is classic p-hacking, where you're sort of incrementally changing things one participant at a time until you literally get what you want and then you stop. Now the reason it's p-hacking is because everything is in the context of random variations. And so as you collect participant after participant after participant, there's going to be some changes in the data that are due to real effects and some changes due to random variation. And if you sort of chase the data at a level of granularity that's that small, then it's pretty likely you were sort of deciding to stop based on random variation and not real effects. So the way I think about it is if you collected 20 participants, things are muddled, let's collect 20 more. Right? Let's collect a chunk more. Just decide in advance how many more you're going to collect. Actually collect that number. and that number should be large compared to the number you've already collected. That would be a doubling in sample size, and then do your analysis, and then sort of you take what you get. Or maybe you collect 20 more after that, but I don't know, there's a gray area, right?
Would you have to call it a separate experiment at that point, or a separate?
Yeah, that's a good question. Would that be a separate experiment? Would that be like a replication, or would that just be adding on to your existing data? I don't know the answer to that. I think different people would answer that differently. I wouldn't think it's I would consider that adding on to your existing data. Although, some people would say, once you analyze your data, you're done. Like, by definition, if you decide to analyze your data, you've decided that's the data I'm going to go with. And if you go and collect more data, you have to consider it a new experiment. Others would say, well, if you collect a bunch of data and you do an analysis and it looks like things are messy, if you collect a whole bunch of new data and you literally do the same thing that you did before, like literally the same thing, and just add more data, then you can still consider that the same experiment. You're just adding on to the same experiment because nothing's changed. These are the gray areas of experimentation and statistics. Yeah.
If we do algorithms, we have to report every time we did it. Like if I collect 20, did it was muddy, then I collect 20 more.
Yeah, so the question is, would you have to report that? Would you have to say, well, so we have 40 participants. What I did was I collected 20, and then I did my analysis, and I didn't like the looks of it, so I collected more. And now here's what I have. I haven't really seen that before. No, but I understand the question, right? In the spirit of being completely transparent about methodology, it wouldn't be unusual to do that. Yeah. All right, well, let's move on. But I think the point I wanted to make was when you're living on the knife's edge and things are messy, then one solution is just to get more data. And the idea, again, is the more data you get, the closer to the truth you get.